Yeah, so that was title of my talk. So I'll first give you a very broad overview of the subject, and then I'll argue that the one-half fractional charges are anyons. They are semions. They are exactly between fermions and bosons. Then I'll argue that these semions give rise to spin charge separation and edge magnetic domains. Then I'll show you that this system, this zigzag nanoribbon, is a topologically ordered insulator. I'll show you that the topological entanglement entropy is finite and universal, independent of disorder and on-site repulsion. Then I'll show you a second evidence for topological ordered state. I'll show you that the entanglement spectrum is identical to the edge spectrum of the system. These two are hallmark properties of topological ordered insulators. And then I'll talk about some possible experiments to measure fractional charges. And I should say that this is not some kind of academical exercise that a theorist has cooked up. Recently, it has been possible to make atomically precise graphene zigzag nanoribbons. There are a couple of papers in Nature. My work was based on Hartley-4 and density matrix renormalization group in the matrix product representation. But this is not going to be a technical talk, so I'll skip all the mathematical derivations. So what is a zigzag nanoribbon? I have drawn here zigzag nanoribbon. These boundary carbon atoms constitute zigzag edge sites. And at the opposite boundary, you also have carbon atoms. Now, if you use periodic boundary conditions on the left and right edges, you can transform this planar structure into a cylinder. And at cylinder edges, you have zigzag edges. Now, if you use Hubbard model and calculate the site magnetization, then you find that the left edge is ferromagnetically polarized, and the right zigzag edge is also ferromagnetically polarized. But those two edge magnetic polarizations are antiferromagnetically coupled. Now, in the absence of disorder, this system is symmetry protected topological phase. This is because of the chiral symmetry guarantees the existence of edge states. What do I mean by chiral symmetry? It means that if you exchange black and white carbon atoms, you basically have the same lattice structure. Now, what is the role of disorder in this system? It turns out that disorder is a very singular perturbation. Ooh, why? I don't understand. Why doesn't it go to the next? Doesn't work? Thank you. So this is the button that I should, yeah.
You will continue.
Yeah, that's what I did, so. Okay, yeah. So let me move on to the next slide. So we know several topological ordered insulators. The best known one is superconductor, and also we know integer quantum Hall states and fractional quantum Hall states. They are all topological ordered insulators. And there's also chiral spin liquids. That is a topological ordered insulator. Now, it's not easy to find a new topologically ordered insulator because there is no symmetry that helps you to find such an insulator. So you have to basically use trial and error method. Now, also one knows that one-dimensional GRAPHENE systems cannot have topological order. This is shown mathematically. The system that I'm considering here is quasi-one-dimensional zigzag ribbon with disorder. So there is a loophole to escape from this theorem. And also, this quasi-one-dimensional zigzag nanoribbon with disorder is a Mott-Anderson insulator with a soft gap, and it is topologically ordered. That's what I'm going to argue in this talk. So the basic physics is the interplay between Mott physics and Anderson localization. And I'll use a Hubbard model to argue this. Okay, now I'm going to show you two slides that are very crucial in my talk. The rest of my talk are just elaborations of these two slides. So let me compare the properties of disordered zigzag nanoribbon and Laughlin states. There are similarities and differences. Disordered zigzag nanoribbon, the ground state has twofold degeneracy, and Laughlin state has n-fold degeneracy, where m is an odd integer. Now, disordered zigzag nanoribbon has 1/2 fractional charge, but the Laughlin state has 1/m fractional charge. Now, suppose you add extra electrons to the undoped system. Then, in the disordered zigzag ribbon case, you get distorted edge spin density wave. In the Laughlin states, you get the so-called hierarchical quantum Hall states. What about edge excitations? In the ribbon case, they are exponentially suppressed. In the Laughlin state, you have gapless chiral excitations. What about the gap? In disordered ribbon, the gap is exponentially suppressed, so you have a soft gap. In the Laughlin state, you have a hard gap. And the most important difference between these two systems is that edge modes are non-propagating in the ribbon system. And the edge modes are non-chiral, okay? Oops. Yeah, this is the next important slide of my talk. So here I have drawn the phase diagram of zigzag nanoribbon. z-axis represents disorder strength, and this y-axis represents on-site repulsion, and this x-axis represents doping. Now, in the inside this yellow volume, fractional charges are well defined, and there are long-range correlations between left and right zigzag edges. Now, in this blurred region, you have fewer fractional charges, and there is no longer long-range correlations. And topological entanglement entropy fluctuates. It's not well defined. So I'll call this region quasi-topologically ordered. Yeah, so now these three figures are just slides of this three-dimensional phase diagram. Yeah, TO means topological order, QTO means quasi-topologically ordered, and NFC means no fractional charges. Yeah. Now, why are there these phases where you have strong fluctuations of topological entanglement entropy? It's basically the effect of Anderson localization. I'll explain in detail about this. So these are basic summary of topological order zigzag nanoribbons. What follows are just elaborations of these statements. So let me explain to you the basic properties of disordered zigzag nanoribbons. Let's first consider non-interacting in the absence of disorder. We can do simple type binding calculation. The results are shown here with the dashed lines. We see that there are many degenerate states near energy zero. They represent edge modes. These modes are localized on zigzag edges. Okay. Now let's turn on on-site repulsion. Then midgap is produced, as I've shown here, and the edge modes are now split like this way. So edge modes are here and here. Okay. Now I have shown here probability densities of edge modes. One is localized on the left zigzag edge, and the other one is localized on the right zigzag edge, like this. Now, what happens if I introduce disorder? You get this kind of bonding and anti-bonding states. So they appear to be split. So their charges appear to be split in half. And this is the graphic, more careful graphic picture of the split gap edge states. Now, you may wonder whether this is a true charge fractionalization. It isn't, because, for example, in double quantum well, you have also bonding and anti-bonding states, and you do not call them fractional charges. Okay? I'll explain later why this cannot be a true charge fractionalization. Now, this is what happens when you put disorder, right? So as I said, you produce gap edge states. There is one more important feature, namely that there is a spin splitting, right? So that's why you get Mott-Anderson insulator. You have to have spin split gap states. Okay, and in the weak disorder regime, you can see the digital states of gap edge states here. And you have soft gap in the middle, okay, like this. Now, it's very important that you have a soft gap in the middle. That protects you, that protects fractional charges against quantum fluctuations. If you close this gap, then quantum fluctuations will kill charge fractionalization. I'll explain this to you later. Oops. Okay, now let's suppose that there are true charge fractionalization. What are the effects of it? Now, there is spin charge separation and domain walls in the zigzag edges. Now, let me explain this. Now, suppose you consider this magnetic domain here. Why is this magnetic domain related to the presence, related to fractional charges? I'll explain that here. These pictures show edge occupation numbers for spin up and spin down. Now suppose you move 1/2 electron from left edge to the right edge. Now, it costs a lot of energy because the density is no longer uniform. It's non-uniform. So energetically, it's costly. So what you can do is you can move fractional charges from right edge to the left edge. Then density is more or less uniform. But then spin is no longer uniform. If you add these two densities, you will see there is a bump here. So transfer of fractional charges are very important. Now, what about spin charge separation? Why do fractional charges lead to spin charge separation? Again, let's imagine that the 1/2 electron moves from left edge to the right edge, like this. And then 1/2 charge moves from right edge to the left edge. Then the resulting spin density looks like this. It's 0 in this spot. So spin is 0, but charge is not 0. And that's what you see here and here. So you have an object that's spin 0 with charge E. This is spin charge separation. Now this is very similar to what's happening in polyacetylene. This is experimental evidence for presence of spin charge separation in polyacetylene. You dope polyacetylene, then you measure conductivity and also spin susceptibility. But strange thing happens here in this low doped region. Conductivity increases, but spin susceptibility is 0. So that means spin and charge act independently of each other. And something similar is happening in the disordered zigzag and nanoribbon. Now, fractional charge are anyons, they are semyons. Now, suppose you exchange 2 electrons, and in this case, it's equivalent to double exchange of 2 fractional charges. So that means this is 1 electron. This is another electron. Each of them consists of 2 fractional charges. Now, you exchange first these two fractional charges, and then you exchange these two fractional charges. The result is that you have exchanged two electrons. And each exchange of two fractional charges gives unusual statistical phase. So this is an ANYON. Okay, now this is some technical matter, but here this picture shows that the topological entanglement entropy is universal. It's independent of disorder strength and on-site repulsion. You can see that it's almost constant. This is for the lower curve is for smaller systems, so there is finite size effect. If you make system larger, fluctuations have decreased. Okay? And the other thing is you could also calculate the entanglement entropy spectrum, and it should be similar to the edge excitation density of states. You can see that it's a Gaussian. This DOS is Gaussian, and also the edge spectrum is Gaussian. These are two hallmark evidence for a topologically ordered system. Okay, so as I said in the beginning, it's not all theoretical exercise. This has a real experimental chance to be observed. And I propose this experiment. You doped ribbon, and you do tunneling experiment like this. This is normal matter, and this is a disordered ribbon. According to our work, if an electron tunnels into the zigzag ribbon, it should divide into two fractional charges. If you calculate the tunneling density of states, you have a peak in the middle. And if I blow up, it looks like this. Now, is this good evidence for existence of fractional charges? Not quite. I mean, there may be some other reasons for this middle peak. So what I propose is you measure the peak value as function of a doping level. And in this case, you see that it shows very strong nonlinear behavior. And I don't know any other system in condensed matter system that shows this kind of nonlinear behavior as function of doping level. What's happening is if you put too much electrons, if you dope it too much, then fractional charges no longer exist. So I believe that this is very strong. This would be a very strong evidence for the existence of fractional charges. Now, if I plot probability density of a state in this peak, you see that the peak is split into two, and there is essentially very little overlap between these two peaks. If they overlap, then fractional quantization is destroyed. Okay, now, this is some interesting physics. Let's see. Here, you see that the fractional states are quasi-degenerate. So quantum fluctuation may destroy fractional charges, but I argue that that's not the case. That's because of Anderson localization effect. What is Anderson localization effect? I don't think many people realize this. Of course, experts in Anderson localization know about this. What this is saying is that suppose you have Anderson localization and two states are nearly degenerate. Then, because of localization effect, they must be physically separated. That's what I'm showing here. These two states have very close energy, but you can see that they are physically separated. So quantum fluctuations cannot destroy fractional charges in this case. Now, in double bond case, you also have nearly degenerate states, namely bonding and anti-bonding states. But here, you see that bonding and anti-bonding states overlap each other very much. They are, hardly distinguishable. So in that case, fractional charge is not well defined. But in disordered zigzag ribbon, because of Anderson localization, they are physically separated. Yeah, and this picture shows that if you dope the system, you get distorted edge spin density wave. This is left edge. This is side spins for the left edge, and this is for right zigzag edge. You can see that you can see spin density waves, very distorted spin density waves. And the other important thing is that left edge and right edge are long-range correlated. Where there are modulations in the left edge, if you have modulations in the left edge, you have also modulations in the right edge. And these two edges are separated. And so they must be long-range correlated. Okay? Of course, you have to have long-range correlations in the topological ordered system. This just confirms that. Yeah, this is my summary. I basically explained this picture in the beginning, so I will not repeat it here. And let me just show you the next slide. I wrote a graduate textbook on topological order zigzag nanoribbon, and I expect it to be published at the end of this year or in the beginning of next year. This book first explains other topological order insulators, superconductors, P-wave superconductors, integer quantum Hall effect, and fractional quantum Hall effect, and spin liquids and anomalous quantum Hall effect. Now, after these, I explain topological order zigzag nanoribbons. Okay, thank you very much.